So this video is about explaining the idea of the thresholding, or the idea of using these string matching algorithms and the compression, the string compression methods to estimate this information dynamics, which is how predictive is the future based on the present based on the past. This motivates us, or the motivation is really to be able to use the string matching algorithms, or the compression methods. And we had one of the homework was using lentil-z, which is a much more intuitive algorithm that actually kind of has this ability to find repeating sequences with variable length. And then we mentioned that there are more efficient ways to do this, like the factor oracle, which we kind of didn't really go into, and I'm not going to ask any questions about actually doing the algorithm itself, parsing it. It's available in the VMO package that we pointed before. But the idea is that we can actually create a structure where we look through suffixes. So kind of part of the idea of all of these prediction algorithms, and somehow also the RNN will do this later on, or we saw that RNN does that. And then I would want to relate this to attention at a certain point, is that we want to take into account past to predict the future or the present. And the way these algorithms work is actually that they don't kind of average everything. It's not like RNN moving your hidden states with some metrics and allowing kind of some memory to be slowly decaying and influencing the past. These algorithms actually are much closer to the attention models, and they kind of look and find where there were repetitions. So if you are here, it reminds you of very specific places that happened before. And this is kind of a general motivations for using these algorithms. So what happens if, and of course you can use them for compression. This is just an example of how an encoding is done using the factor oracle instead of the lentil-z, and kind of takes into account more of the overlapping structures, and it kind of achieves more efficient encoding more quickly than the lentil-z. So the idea was that we could actually now use the difference between, the number of bits, the size of the alphabet, and I'm still talking about sequences, right? So there is no like audio signal and features. We all operate at this point on top of a finite alphabet. So this is all symbolic, okay? But the whole idea is that we could use this idea of computing this mutual information and choose between different candidates of symbolization. So that's kind of the context where we were using this method. Was all the string matching algorithms are great, but they require a finite alphabet. You have to work on in a symbolic domain. Now, what happens if you want to work with audio features, which are vectors, and they basically have real values? So there needs to be some kind of a distance measure or something else that guides you. Or you can go and cluster them, or symbolize them, and turn your continuous measurements into alphabet, right? You create them. You create basically some kind of encoding over a finite set of states. But I mean, how can we do that? I mean, we don't have really good guidance on taking, let's say, audio features, Melcapstra, or you can pass this through some encoder. But again, your output are continuous values. And now how can we basically now learn the temporal structures? So the idea was, well, if we have a candidate encoding, and we have a way, like some kind of candidate symbolization, we can apply the string matching algorithms, and we can basically measure how efficiently they encode the sequence. So if we take the size of the alphabet and log of this, log base 2, this will be our reference. This is basically how many bits you just need to encode if you consider every instance of your state, or the whatever the alphabet, basically the letters encode the states. That's how many bits you would need just to encode each one individually. On the other hand, you can use compression algorithm and the factor oracle, but this is really a general principle. If you consider this, the entropy of your current based on the past, as some kind of a basically an abstract representation of what the compression or predictive compression tries to do, because we try basically to use all the past information to predict the present or the future, and this is what these algorithms do. They use they repeated the suffixes, they use the repeated sequences that they find to predict the future, and that's how they encode. So if we basically in good faith say, yeah, we'll be happy with the way you compress, the entropy, this conditional entropy is in some sense approximated by just saying, well, let's see how many bits your compression scheme allows us to do. So this is kind of a, I don't know if we call it a cheat. I don't know if it's a cheating or it's smart, but this is kind of the idea, the trick. Okay, the trick is we don't know how to estimate this. We approximate this just by considering the size of the alphabet without compression, log of the size of the alphabet as our entropy, the baseline entropy, and the number of bits using a compression algorithm as our estimate of the conditional entropy. And the difference is basically this information dynamics, information rate, sometimes called, which is the information that passing from past to the future. Now, we can get a number like this for every symbolization level. So at least in the VMO, the trick is that now we basically go and we search over all possible thresholds. So our clustering is a little naive. We basically look at all the points, all the features, and we basically kind of decide that if a threshold is less than some distance, the next point, that because it's incremental, the next appearance of some data point will be symbolized or classified same as the previous one if it's close enough. Okay, so this is basically kind of just a summary of this whole idea. We basically create a different graph for every threshold. Okay, and for every graph we estimate the information rate, and this is what is described in these two or these three pictures. Okay, is that if we have a very low threshold, okay, which means that we classify every data point, and this is done in basically one-shot way. This is just one single musical piece. If every whatever the feature is here, capture coefficient, is different for every instance, so this is time. Basically, we encode each one separately, so we have no, in that specific graph representation of the factor oracle, we have no repetitions. Actually, if we want to reach a certain value, a certain instance of a spectrum, you actually have to jump there, because nothing, I mean, at that level of resolution where we are so sensitive, everything is new. The opposite is here. If our threshold is very high, what we have is these repetitions. So every point is the same as the previous one, the same as the previous one. These are the suffix links, and they become basically, if you see this structure, you know that basically your threshold was high, or basically what you have in this symbolic sequence now is just one letter keeps repeating itself. And then the idea was, well, probably the right symbolization or the right way to take a continuous signal, extract features, and then create a symbolic sequence. and the symbolic sequence we're seeking is such that it compresses the best, would be some kind of a trade-off or some kind of compromise graph that has this interesting structure. So that was kind of the whole idea of using the threshold, okay, or searching for the highest prediction or the best information rate, the highest information dynamics or information rate, by changing the thresholds and quantizing your original audio features into different alphabets, or the number, of course, of the symbols, or the number of clusters will increase. Sorry, it will decrease with the threshold. So when we have very fine threshold, we have huge alphabet. Here we have just one symbol. Now, why intuitively we have 0 here and 0 there? Basically, what we have is this phenomenon, right? If the threshold is very low, right? We have a very high, we have big alphabet, right? We have huge amount of possible states or classes or symbols to take our continuous features and label them. So we have a huge amount of labels. Basically, every frame gets a different label. So our alphabet is huge. So this entropy is high. But then the number of bits becomes the same. We don't manage to use the past. Okay, so if the past doesn't tell us anything about the future, the entropy, the conditional entropy becomes same as the unconditional entropy. So hx given the past will be same as hx. So these two terms will be same, and this will be 0. So at very low threshold, just because we cannot predict anything, the mutual information of your present and the past is 0, because we cannot use the past in any useful way. What happens here, okay, if we go to very high thresholds, basically our entropy here, so it might be very, very well predicted, right? The past will predict the future. So this will be close to 0, right? But also our alphabet becomes very small. I mean, if we have only 1 or 2 or whatever, just a small number of instances, there's very little entropy, very little bits, because if you consider everything the same, then there is no uncertainty. So even though this is very good, this is also very small. So this is goodness, this is small, and this is small. So both of these factors will decrease as we increase the threshold, and eventually you will have both of them so small that it will hit the 0 again. So that was kind of the idea, that there is some kind of an optimal trade-off between how predictable things are and how basically complex you have, how many details you have to take into account when you think about the music representation. And yeah, so we use this criteria in different ways. And I think this is kind of the explanation of this whole idea of trade-off, or using information dynamics, or using information rate to optimally symbolize audio features. Now, I'll mention a little bit about this also in my next set of slides, but I hope this kind of answers this notion of this trade-off between looking for structure in time versus the amount of detail or the precision with which you basically describe every instance. So if you think about this as some kind of a lossy representation, then somehow there is an optimal representation here. Too complex a representation doesn't have good prediction, and too simplified representation will be basically also not telling much about well, it will tell a lot about the future from the past, but the task itself, the complexity of the task is so small that it doesn't really have a good use. So that's kind of the principle, that moving from a continuous world to some kind of a latent states, and especially if you need to cluster them and represent them as symbolic sequences, because this is kind of the way you can use string algorithms to take into account variable memory length, and that's slightly different from what the RNNs do, and we'll talk about this in the context of attention in a second. Okay, so if there are any questions,